Safety Analysis of Vassar Train Bridge by James DeVolder, Luke Hopkins, Joe Vandenputty. All of us are mechanical engineers at Kettering University. Our objective is to determine whether the bridge is safe when maximum loads are applied to it. The background of the bridge is a railroad bridge located in the southwestern part of Vassar, Michigan. The bridge was constructed prior to the town of Vassar, founded circa 1903. The assumptions that we made were that the max weight of the train is 210,000 kilograms, the weight of the bridge is 100,000 kilograms, the bridge is a simply supported structure, cross-section of bridge is rectangular, bridge is made of structural steel, analysis of bridge is completed in 2 dimensions, force is evenly distributed across the surface of the bridge, the top surface was assumed to be negligible in the cross-sectional area, which means that the wood that's on top of the bridge is negligible. Local acceleration due to gravity is 9.8041 meters per second squared. And then to the top right, we have our model, our diagram. It shows a simply supported structure, simply supported bridge, which has an even distributed load across the top. And then our cross-sectional area is 0.4064 meters across and 2.06 tall, which is made out of structural steel. Our methodology was to first find the max weight and distributive force. Next, the free body diagram was constructed along with shear force and bending moment diagrams. Next, maximum shear and normal stress were calculated and plotted according to Moore's circle. Lastly, the factor of safety was calculated and plotted along the length of the bridge.
To the top right, you see the shear force diagram with force on the y-axis in newtons and length on the x-axis in meters. It starts off with 1.5 meganewtons and it decreases to negative 1.5 meganewtons linearly across the bridge. In the center, the shear force is 0. To the bottom left of that, you see the bending moment diagram. It starts and ends at 0 and curves in a parabola, a negative parabola shape, to a maximum of 6.8 meganewton meters. The y-axis is in newtons per meter, and the x-axis is the length of the bridge in meters. To the left, you see the factor of safety plot, with the factor of safety plotted on the y-axis, and the length of the bridge in meters plotted on the x-axis. You can see it races off from infinity, dips down to a minimum of 8.35, and then races off to infinity at the edges of the bridge. For Moore's circle, you can see the 2 points that were plotted, with the normal stress being 0 for the point on the left, and the maximum normal stress that we calculated being 47.83 megapascals. The force we calculated for the bridge is 3,000 kilonewtons. The distributed load across the bridge is 170,000 newtons per meter. The shear stress that we calculated was 5.46 megapascals, and the normal stress that we calculated was 47.28 megapascals. The maximum shear stress that we calculated was 24.26 megapascals. The minimum normal stress was 0.62 megapascals in compression, and the maximum was 47.90 megapascals in tension. The factor of safety that we calculated was 8.35 times the recommended load.
The goal of this project was to determine whether the bridge in question is safe by finding the max stresses on the bridge. The bridge was simplified into a 2-dimensional representation. Max shear and normal stresses were determined and plotted along the length of the bridge. These values were then used to calculate the factor of safety in order to determine how safe the bridge is. The bridge is safe with a factor of safety of 8.35. These findings are only valid for the assumptions made above. Here are our references. Then here's a selfie.